Alright, so last video we were looking at the last example in 2.5 was exercise number 46. Okay, and that was kind of a lengthy one. See if you can get through that. It's good practice to see if you can. Let me know if you have any questions about that. I want to get to a critical application of continuity. And the way it works is the following. This is the way it works in practice, in fact. Suppose I've got some function, and I know my function is negative at some point, so I know it does this somewhere, and I know it's positive at another point. Then, if f of x is continuous everywhere, what needs to be true between these 2 points? Well, what has to be true is that if f is continuous, then f must cross the x-axis somewhere in between. Okay, and so let me state that over here. So if f of a, let's see, I want to say f of a, this is my a here and this is my b. I want to say that f of a and f of b are different in sign, sign. So this one's negative and this one's positive, or it could have been vice versa. It could have been positive and negative, right? And so I'm going to say if f of a times f of b is less than 0, so they're different in sign, and f is continuous on the interval from a to b, then there is a value of c on the x-axis such that f of c is equal to 0. Okay, this is really an important theorem. Now, I should say that the general theorem we're going to use is actually a little bit the theorem we're going to use is a little bit more general, is what I want to say. So what is our theorem going to look like? Our theorem is going to look like the following. Suppose that I have a number, I'm going to call it n on the y-axis. Here, by the way, the number was 0. And suppose, in addition, that at some point a, the function is below n, and at another point b, the function is above n. Can you say what's going to happen? Then, if f is continuous, there must be at least one c such that f of c is equal to n. You see how these two things are really the same? Okay, this number n here is going to be called the intermediate value. And our theorem is called the intermediate value theorem. Okay, so let f be continuous on the interval from a to b, and let n be any number between f of a and f of b. So therefore, one of these numbers is smaller than n, and one of these numbers is bigger than n, right? Then there exists at least one c on the x-axis such that f of c equals n. Good. That's really an important theorem. I've said that several times. Let's see why. So let's see how this theorem is used. So here's an example. Prove that the equation x minus 5x minus 5 sine x equals pi has at least one solution. Okay, now notice that this does not tell us that we have to find the solution. We just want to prove that a solution exists. And so the way to do this is to actually just plug in some numbers and see what happens. So let's try, by the way, the pi here is going to be our n in the intermediate value theorem. Let me bring that down again. And so I'm going to just start in trying a few numbers to see what happens. Let's see, f of 0, if this is my f of x here, would be 0 minus 5 sine of 0 is 0, so 0 is less than pi. Let's see, f of 1, if I plug that in, is going to be minus 3.2, which is still less than pi. F of 2 is approximately minus 2.5. That's still less than pi. I'm getting a little bit higher. How about f of 3? I'm just trying out a few numbers here. That's going to be 2.294. That's still less than pi. I keep going. F of 4 is equal to 7.78 something. Hey, there it is. Boom, 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 boom. Right? Because pi is between 2.29 and 7.78. Therefore, our solution is between 3 and 4. So let me say that again. In what we computed, we know that f of 3 is less than pi and f of 4 is greater than pi. Therefore, by the IVT, the intermediate value theorem, there must be at least one value of c, such that f of c equals pi. Right? That gives us our solution. Good. Okay, let's try one more. I think we've got time for one more. Example is, this is number 59. If you want to follow along. Show there is a number whose cube is one more than the number itself. A little bit of a story problem. So whenever you're dealing with a story problem, it's good to label your information. So let x be the number. Then just translating this equation, the cube, so x cubed, translates to equals 1 more than the number itself is x plus 1. Good. Now, if I have a function equal to a function like this, it makes it hard to directly use the intermediate value theorem, because the intermediate value theorem has your function equal to a number. And so rather than having function equal function, what we do is instead show there is a solution to the equation x cubed minus x minus 1 equals 0. Okay, and so this is going to be your function f of x now. And how do we do that? Well, if we're on the x-axis here, we just start plugging in some numbers to see if we can get f of x below and then f of x above the x-axis. So let's just try a few nice ones. let's see, what is f of 0? Notice I'm starting with 0 a lot. That's negative 1, so that's negative. How about f of 1? F of 1 is 1 minus 1 minus 1. Whoops. So that's still negative. How about f of 2? F of 2 is 8 minus 2 minus 1. I think we finally got it. Positive. Good. So therefore we know that this is 1 and this is 2. And so by the intermediate value theorem, notice that f is continuous because it's a polynomial. There is a c, or a solution, in the interval, in this case, from 1 to 2, where f of c equals 0, which is the solution to our problem. Good. All right. That's probably enough. We will maybe look at more examples later. I think this is enough for now. I think this will get you through the homework anyway, and let you think about continuity. Okay, see you later.